Okay, so let's start. Welcome back after the weekend. And so we will continue. So we started this beautiful topic of Laplace transforms in the last class, last Thursday. And all the remaining classes will be on Laplace transforms and then using it to solve differential equations. So you will get the first hint today. How are we going to? So today also no differential equations coming to the lecture, but you will get the first hint today how this is going to be useful in solving differential equations. Okay, so let's start the lecture. Let me start sharing the screen. And as usual, one of you please confirm that you can see it.
Yes, sir.
Good. So let's start. Again, Laplace transform. So all the remaining topics will have this only. I mean, it will be Laplace transform. Okay. Very important topic, very beautiful topic. So we have started this topic on last Thursday. And let me quickly recall and then continue. So remember the definition and remember the notation first. So this f is a function defined from where to where? This f is a function defined on
0 to infinity.
0 to infinity and valued in
Real value function.
plus codomain is r, and L of f is the Laplace transform. I stress that you can define it on a complex variable, but from today onwards, I will not put real part, etc. I will just take it as a real variable, having made the point last time that it can be defined on a complex variable. And I don't know about the applications that you will have in your other courses, but sometimes it may be important that it's a complex variable. But the theory is parallel, so I might restrict myself to S equal to R. And this was one notation. And what is the other notation I said for L of f?
Capital F.
Capital F.
Very good. Okay. So what was the definition? This is integral 0 to infinity. That's where t is defined anyway. T is from 0 to infinity. And you take ft and you integrate it against this function e power minus st. So even if s is a complex number, this makes sense. Of course, it may converge, it may not converge. And you have to take the region in which it converges. So last time I wrote real part of s is positive. Now I'm only writing s is positive. Wherever I write any condition about s, if you want to think about s as a complex variable, you just put real part. It will go through. Most of it will go through. Okay. So the constant function had Laplace transform 1 by s. What is the next function that we did last time? After this was our first example.
Exponential.
In the order in which we have done, let us recall, next thing was exponential. And there the answer is 1 by s minus a. And this was defined for s bigger than a. What was the third example?
Sine.
Sine, cos.
Sine 80. And sine, the answer was a by s square plus s square. And then we had three examples which I did not do. I asked you to do.
Cos 80, cos hyperbolic 80, sine hyperbolic 80.
And what are the answers for cos 80? What is the answer?
S upon x square.
S by s square plus s square.
And cos h80, what is the answer?
S upon s square minus s square.
Very good. And this, did you check whether this is required? Okay, otherwise please do check. I think it is required. And sin h80, what is the answer?
A upon s square minus s
square. A upon s square minus a square. So for sine, whether it is usual sine or the hyperbolic sine, the numerator is a. And cos, whether it is usual cos or hyperbolic cos, the numerator is s. And in usual sine and cos, the denominator is the same. And hyperbolic, the denominator is the same. Okay, so these were the basic examples. Didn't we do one more example?
Yes.
Was
t to the power n.
T power n.
T power n, or more generally t power
Alpha. Yeah.
Any real number p, where p is bigger than
0.
Minus 1.
minus 1. P is bigger than minus 1. So this is what I will recall now. So gamma function was
Gamma
like this. Yes, using the gamma function. This was the definition. What was a crucial step in proving the convergence? I did not do it all that rigorously, but I gave you the main hint. What was a crucial step in proving the convergence of this integral?
We broke
It
it into two
Add
parts.
1 to infinity.
Yeah. And what were the parts? What were the best parts to take?
0 to 1 and 1 to infinity.
0 to 1 and 1 to infinity. Okay. In 1 to infinity also you are actually dividing it to 1 to some large number and that large number to infinity. But basically the idea was 0 to 1 and 1 to infinity. Using that we did the convergence. And then we had a functional equation. Did I use this word functional equation? Yes. And what was the functional equation for the gamma function?
Gamma of y plus 1 equal to y times gamma y.
And what was the main idea of the proof if you have to give the key sentence?
UV integration means
By
integration by parts.
Integration by parts. So integration by parts gives you functional equation. And so the answer for this word proof question mark is integration by parts. Okay, I have written it here. So integration by parts. And why did we introduce this? There are two reasons.
because it comes up in the Laplace transform.
Yes, that is the real reason for this course, that it came up in t power p is a very natural function, right? I mean the power function, and in its Laplace transform gamma function came, so we had to introduce. And what is the aesthetic reason for which we introduced it? Even if it was not coming in Laplace transforms, it was not that, yeah,
factorial for negative.
yeah, it interpolates factorial function. So it's a nice idea, and of course we needed it in the theory of Laplace transforms. Okay, so let me recall that example also. L of t power p for p bigger than -1. This was a definition, and we made this transformation. Therefore, L of tp, you change the integral, and now you notice gamma function is here automatically. This is 1 by s power p plus 1 e power minus x power p, but this is the definition of gamma of p plus 1. And all this made sense whenever s is positive. And yeah, so and we did in particular for n a natural number, gamma of n plus 1 is n factorial. So you got this, and you could also do things like this. So t power minus half has gamma function, has Laplace transform root of pi by s. Gamma L of t power half is root of pi by 2 times s power 3 by 2, etc. This is where we stopped last time. This is exactly the last slide of the last lecture. Okay, so let's continue from here. So the main point is, how do you know whether LF will exist or not? What is the meaning of whether LF will exist? Whether the integral makes sense. If the integral does not...
Converge integral.
Say that again.
Whether it converges or not.
Yeah, whether it converges or not. Exactly. LF exists meaning the integral makes sense. Therefore, you can do many things using that. Does not exist meaning the integral may not converge. So this question we have to answer. So let's spend some time on this. It is natural to ask under what conditions convergence is guaranteed. Okay. You want sufficient conditions. Look, if you put this condition, then you prove integral converges. If you put this condition, then you prove integral converges. We are not saying that integral converges means that condition is satisfied. We are not saying it is necessary. We are going to put sufficient condition, at least one sufficient condition under which we know that the integral converges. The point of such results is that the sufficient condition in practice will be easy to check. And therefore, you can conclude that the integral converges. Okay. So one such condition is actually two conditions here. No, one condition. One condition has two parts and both of this together. Okay, so what is the key word here? Piecewise continuity and exponential order together. So if the function that you take is piecewise continuous and also of exponential order, both together, then the Laplace transform, the integral converges, and therefore the Laplace transform exists. Do you know these two words? You know piecewise continuity, right? You know continuity, continuous functions on an interval. So the rest is plain English word piecewise. I don't know whether there should be space between piece and wise, but what is the meaning of piecewise differentiable or piecewise continuous? Any
Functions with
property P, if you say piecewise that property, what does that mean?
function with a discrete number of discontinuities at which we have to break the integral.
Yes. And in the remaining parts, it is continuous. And this is correct. This is the English meaning. But in mathematics, we are going to add one more word, that at the points that you break, the continuity can be of different types, right? It has to be one of the simplest type of continuities. What is called? What is the simplest continuity that you know? The simplest discontinuity that you know?
That it jump discontinuity.
Jump. Yeah, it is just like a step function, a jump. Okay, jump discontinuity. So piecewise continuous for us in this course means it could be discontinuous at finitely many points on your interval, but at all those points, the discontinuity is a jump discontinuity. You know, fx equal to 0 till here and 1 from there. That kind of discontinuity. Only that is allowed. And exponential order is something that you may not know. How many of you have seen this definition of a function of exponential order? Maybe not. Let me introduce this. Okay, so what does this mean? Piecewise continuity is just that possible discontinuities are finite and they are jump, and a function f. So this is a key definition in this slide. A function f is said to be of exponential order if something satisfies. Something is satisfied. And what is that? If there is a real number a. See, exponential order means exponential function may come in the definition, and exponential function is e power at for some a, and that's what I am saying. There exists some a such that the function is bounded by e power at. So there is some a such that the function is bounded by e power at, well, not quite, up to a constant k. And where is this bound happening? This bound is happening after some stage. For some m, anyway, t is, we are considering all our functions are defined on 0 to infinity. So t is anyway bigger than 0. And I am not saying that this bound exists for all t bigger than 0. I don't need to demand that. I need to demand only after a stage. So there is an m beyond which this is satisfied for some a and for some k. Is the definition clear? So I say that a function is of exponential order if beyond a stage, meaning there is a capital M, and beyond that, it can be bounded by an exponential function e power at for some a up to a constant k, positive. Should I repeat the definition? Is there anyone for whom the definition is not absolutely clear?
Yes, sir. I didn't understand. 1 second.
So what I'm saying is this is the definition of exponential order. That means modulus of that function should be bounded by e power at for some a. E power at, when I say, there is always that a, no? So that's why I'm saying there exists a such that it is bounded by e power at. Not quite bounded by e power at, 1000 times e power at is good enough, 1 million times e power at is good enough. This constant doesn't matter to me. Up to some constant multiple. Okay. And the final thing that I'm saying is I don't want this throughout 0 infinity. My definition only demands that this is true beyond a stage. There is a stage beyond which this is true. For t bigger than or equal to m, such an inequality is true with constants k and constant a.
Sir, if it holds from 0 onwards also, no problem.
No problem, in which case m is 0.
I mean, you give m greater than 0, no?
Yeah, that is because t is also strictly greater than 0. Usually, I'm taking t from 0 to infinity.
Sir, in this case, what is there any order for the function? First or second order?
Okay, maybe you can say that a is the order, but we don't usually say that because the word order tells you some natural number, whereas a could be a real number. Yeah, but you can say that a is the order.
Sir?
Yeah.
Can I say like e power x sin x like that? E power x sin x is exponential order?
Well, you have to check whether this condition is satisfied.
It is bounded by e power x from upper and e power minus e power x from down, no?
E power x?
Sin x.
Sin x is down or sin x is in the...
Sin x is down. Sin x is down.
Okay. Then of course it is. Okay. Yes. So that's a good example that you are giving. If you take ft to be e power t times sin t, then modulus of that is less than or equal to e power t. So what is your a? Obvious a is 1. and obvious k is
K can be any value greater than.
any value greater than 1. So the optimal k is 1.
Mm.
Okay. So therefore, you have given me an example of a function of exponential order. Clear, no? So let's do some more examples. First example, if ft is bounded beyond a stage, then of course it is of exponential order. It need not be bounded, up to a stage. Only in a finite interval 0 to m, it could be unbounded. But after that, if it is bounded by a constant, then it is exponential order. Exponential order. What is the order of this function? A equal to
0.
a equal to 0, because k meaning k e power 0t. Okay. And next example, if you take hyperbolic cosine, you can write it as e power t plus e power minus t by 2. It is less than e power t everywhere, right? Agree? So
Yes,
this
sir.
is less than e power t, therefore it is of exponential order. If you take t power n, do you agree that it is less than n factorial times e power t?
Yes, sir.
Yes, sir.
Because e power t is summation t power n by n factorial, and this is just one term. And therefore, t power n is of exponential order, and therefore any polynomial is of exponential order. Because if you have two things of exponential order, then their sum is also of exponential order, right? If f1 is of exponential order and f2 is of exponential order, is it clear that f1 plus f2 is of exponential order?
Yes, sir.
Because f1 will be less than or equal to k1 e power a1t, and f2 will be less than or equal to k2 e power a2t. You can take maximum of those constants and maybe multiply by 2 or something if necessary. And then you have e power a1t and e power a2t. One of them may be dominating. Take the dominating thing, and you can write mod ft is less than or equal to twice that constant times e power the dominating one. So sum is okay. What about scalar multiple? If f is of exponential order, is it true that 1000 times f is of exponential order? Obviously, the constant will be multiplied by the appropriate constant. That's all. Okay. So scalar multiple of exponential order is of exponential order. Sum is also of exponential order. Therefore, Therefore, if t power n for any n is of exponential order, then it follows that any polynomial is of exponential order. Okay, so it's an interesting class of functions. And next example, e power t square is not of exponential order. Okay, there's no way you can put this less than e power at for some a beyond any stage, because t square grows much beyond at. At is linear in t square is quadratic in t. You will not be able to bound. You can give a proof, and therefore this is a function which is not of exponential order. And this I already said, sum of functions of exponential order is also of exponential order, and this we have already used here. Yeah,
How can we prove that e power t square is not an exponential order?
you have to do it. I am just giving you the basic idea, because t square grows faster than at for any a, and therefore you don't expect that to happen, but you need to prove it. But this is the basic idea, that t square is growing fast. T square is quadratic, it grows faster than a linear function in t. You have to use that idea and try to give a proof. Okay.
Need to go by reverse. I mean, assuming it exists and then prove it like that.
Yes, exactly like that. That will be the easiest way. But intuitively, it's clear, no?
Yes.
Suppose, I don't ask for a proof. It's an objective type question. And I ask you whether this is of exponential order or not. What will be your answer?
No.
No, right? Because you get that feeling, because t square is bigger than at for any a beyond a stage, right? There is always a stage. See, t square for small t may be less than 1000 t, but beyond a stage, that will not be true. T square will overtake at for any a. Correct? That is the reason. So you would write down a proper proof. Okay. So now let us see why it will be. Yeah, let us see. So I only asserted that if you have piecewise continuity and exponential order, then what is my theorem? My theorem is that Laplace transform
Is converging.
integral is convergent. In other words, Laplace transform exists. Okay. So let me assume that ft is piecewise continuous on an interval 0 to alpha, for all alpha positive. Yeah, so I'm not saying on one interval. I'm saying that all such intervals for all alpha positive, I know that this is piecewise continuous on this. This is just a way of writing. See, piecewise continuity I define only on an interval. In other words, I am saying that it is piecewise continuous throughout 0 to infinity. But that's not how one says it. So I have used this formulation 0 to alpha for all alpha positive. Okay. Basically, I'm saying ft is piecewise continuous everywhere. And further, suppose it is of exponential order. This is just the definition of exponential order, right? Ft is less than or equal to k e power at beyond a stage for some constant k and some constant a, and that stage m. Okay, so this is true. And now what should be my claim? My claim is that the integral converges. And if exists, so integral converges. Okay, so let me assume for the time being that the function is, see how do you develop an intuition for the proof? What will be the reduction step? Suppose you don't assume piecewise continuous, but you assume that it is continuous itself. Then how will you show that? Suppose f is continuous everywhere. How will you go about?
We can split it from 0 to m and m to infinity.
Yes.
And we have to choose s to be greater than a. Then we can.
Yes.
proceed.
Yes. So what is the key word now? This is correct. And after, so 0 to m, you don't have to worry because it's on a closed interval and f is continuous, e power minus st is continuous, and therefore Riemann integral will exist. M to infinity, you need to give a proof, and you are saying s bigger than a you will use, and you may also use integration by parts, right? Which is what we have done earlier. So that is the proof. Now suppose it is piecewise continuous, not continuous, but only piecewise continuous. How will you prove it now?
Taking into intervals again.
Yeah.
Continuous parts.
Intervals. At each interval, your proof is correct, and you club all those together. Therefore, you have proof. So it's easy. Okay. So you have, this is the definition: 0 to m plus m to infinity, and f is piecewise continuous on 0 to m. Because why is it piecewise continuous on 0 to m? This is where I'm crucially using this fact. It is piecewise continuous on any 0 alpha is given for all alpha positive. So whatever is your stage m, piecewise continuity is there, and therefore dividing it into finitely many things, it is continuous in all those intervals, and in all those intervals it converges, and it will be a finite sum of those things. Therefore this converges. So this exists. Okay, now we have to do m to infinity e power minus st ft dt. This is convergent, and for that, for t bigger than or equal to m, you have e power minus st ft modulus. What can you say? Beyond the stage, what is the property of the function f? F is less than or equal to, mod f is less than or equal to
K e power at.
e power t.
Therefore, this is less than or equal to e power minus st times k e power at, which is k e power minus of s minus at. And where will the integral converge now? The integral of this
S greater than a.
S minus a greater
converge when
than a.
S is greater than a. So I'm underlining this: for s bigger than a, this integral converges, and therefore integral of the modulus converges, right? Because modulus of this is less than or equal to this. So if this converges, if f is less than or equal to g, and if integral g exists, then integral f exists. Therefore this exists, and therefore this exists. Why? If this exists, then this exists. Why?
This is upper and lower bounded by the. This integral.
You know that the integral of the modulus is less than or equal to modulus of the integral. No, modulus of the no. What is the way? Modulus of the integral
Reverse.
is equal to integral of the modulus, right? Modulus of integral hx is less than or equal to integral of mod hx. So this integral is anyway less than or equal to this integral. Therefore, if you can show that this converges, then of course this converges. Is the proof done? Proof is done, no? Because here we split it into two cases. First one we use piecewise continuity, and second one we used exponential order. And therefore both.
Sir?
Yeah.
We written s greater than a, no?
Yeah.
For taking for being convergent.
Yes.
That a is chosen by us, no? Actually.
Yes. Yes.
Then we need to choose the least possible a, right?
Yeah, so what I'm saying is, so the correct statement is, very good question. Further, suppose this is true for some A that is given to you. So what is an absolutely correct statement? Not LFS exists, but LFS exists, and I should continue this sentence for
For s greater than a.
absolutely. Okay, I deliberately made this mistake here, and I'm not going to correct it in the slides also. That is why I went back and underlined it here. Okay. So yesterday I wanted to either underline here or state it correctly in the theorem. I wanted this question to be asked and stress it. Okay. So I'm not going to make this correction, but I'm making the correction verbally. What is the absolutely correct statement? LF exists for S bigger than A, and this is going to play a role later. Okay.
The domain is not 0 to infinity. That means only from a only it will run that domain.
No, domain of function. Yeah.
Function L of f. That Laplace.
The domain is, yeah, correct. It is not 0 to infinity. A could be negative also, no? It could be a negative number also. For whenever S is bigger than A, that is the domain. So
Yes.
A to infinity is the domain.
Okay.
Okay. And if S was complex number, what will be your condition? For real part of S is bigger than A. That will be your condition. Real part of S is bigger than A. So it will be a right half plane. Okay. Clear?
Yes, sir.
Okay, good. So that is clear from the proof. S bigger than A is crucially used. If S was complex, here you will put real part of S is bigger than A and everything will go through. Okay. So now we know many functions for which Laplace transform, you know for sure it will exist. If my function is any polynomial, clear, no? Because polynomials are of exponential order, they are continuous, therefore Laplace transform exists. Okay, so remark, conditions in the theorem are sufficient. Can you complete my remark? When the English sentence starts like this and when it is a remark after proving that theorem, what is your guess?
What am I saying? Polynomials or Laplace transform of polynomials converge.
Sufficient and necessary.
Yeah, that polynomials exist anyway is clear. We already said that. I'm making a new remark. I'm telling you something new.
Not necessary.
It is sufficient. Of course, the remark could have continued in both ways. I could have said that are sufficient and also necessary. But another way of continuing is are sufficient but not necessary. What is your guess? You know, I could have continued saying are sufficient, which we have proved, but are also necessary, but that is not obvious. It is beyond the scope of this course, right? I could have continued my sentence like that. Or I can continue the statement by saying are sufficient, but not necessary. Here is an example. What do you think I'm going to do?
Not necessary.
Not necessary.
Necessary.
How did you get that feeling?
We are assuming that it is exponential order only, compound. Not all functions are exponential.
I don't think there is a rigorous answer to that question. Yeah, but
Theorem states it is from closed zero.
yeah. So you got, yeah, correct. That's a good point. So you got some idea, and that's exactly what I'm saying, but not necessary for the existence of LF. I should give an example. Here is the example. This example we have already done here. Let me go and show that example. In this slide, look at this. L of t power minus half exists, no? And the answer is root of pi by s. And what is the condition on s? S is bigger than 0. So whenever s is bigger than 0, t power minus half has a Laplace transform. But is it piecewise continuous? Is it piecewise continuous? Near 0, it is not. When t going to 0, yeah, so I must, yeah, so it's not such a great example either, as I realize now.
Sir, in the theorem, you use a closed interval 0 to alpha.
Yeah, that's what. So you have to use closed interval 0 to infinity to say that this is not piecewise continuous. Okay, but so in which case it's not a good example, no?
So this is an improper integral when we try to evaluate the Laplace transform, whereas there you use the properties of a proper Riemann integral to conclude it exists.
No, this is fine. This is fine. See, S is positive. S is positive, and for S positive, okay, so my notation, this should be bracket S here. L t power minus half cannot be this. L t power minus half bracket S is this. And t power minus this function, if you consider on closed interval 0 to infinity. So what I mean is, you consider a function you consider a function on closed interval 0 to infinity, where at t equal to 0, you define it as some number, and t is bigger than 0, you define it as t power minus half. Is that function piecewise continuous? T equal to 0, you define it as 1, and t bigger than 0,
No,
you
sir.
define it as
It
t.
does not have. It
Is it
has
piece-
the infinite discontinuity, right?
Yeah, it is not jump, because the jump is not finite. Okay, so it is not piecewise continuous, but still the Laplace transform exists for that function, because t at t equal to 0 will not matter, no, because in integration 1 point will not matter.
But is it of exponential order, sir?
Is t power minus half of exponential order? Check. I think it is of exponential order, right? Because
It is
beyond
always
a stage
positive.
only will matter, and beyond a stage, can't you bound it? It is of exponential order. But please double check, okay? I'm not
Yes,
thinking.
sir. First, after greater than, we can take from some mn, we can say that.
Yeah. And that is the definition of exponential order, no? Beyond a stage
Sir,
only matter.
after m, we can say it's exponential.
And after m, no. So if after m that condition is satisfied, then you will not say after m only it is exponential order. After m, if that condition is satisfied, our definition is it is of exponential order.
Yes, sir. Then t power minus half is of exponential order. No?
Yes, t power minus half is
Not
of
exceptional,
exponential order, but it is not piecewise continuous, and therefore it is a counter example to the theorem, because not counter example. I'm saying it is the condition is not necessary, because sufficient condition was piecewise continuous and exponential order. Okay, so
Both should be satisfied. Sufficient condition.
it is sufficient but not necessary, we are proving, because this function is not piecewise continuous on 0b for any b, but Laplace transform anyway exists. Okay, now you can ask me for one more counter example. No, what will be the shape of that counter example? Here this is of exponential order but not piecewise continuous, and then I show that Laplace transform exists though it is not piecewise continuous, showing that piecewise continuity is not necessary, it is only sufficient. What should be the other type of counter example?
Not of exponential order, but it has a Laplace transform.
So it may be piecewise continuous, but it is not of exponential order, but still
Laplace transform exists for some.
Laplace transform exists. Okay, so not of exponential order, still Laplace transform exists. I don't have an example right now, but a hidden example will be there in today's lecture. So I ask you to stop me and say, when we are going to continue our lecture. We have some more time. And at one point, one of you should stop me and say, look, here is your example that you asked for. Okay? The game is clear, no? What I'm expecting from you is clear. Here is a function which is not piecewise continuous, but still Laplace transform exists. You will naturally ask for a function of not exponential order, but still Laplace transform exists. And I'm not saying, look, here is a function, but when we continue our lecture, naturally there will be an example, and you should remember this answers that question. Okay, at that top point, you stop me and tell me. So let's continue. And one is an obvious thing. If f and g are functions such that LF and LG exist, complete this theorem, complete the statement.
Laplace transform of AF plus BG will exist.
Absolutely. Laplace transform of AF plus BG will exist. I'm just proving. Yeah, exactly. And not only that it will exist, LF AF plus BG is A times LF plus B times LG. Is there anything to be proved here? It's obvious, no?
What about f into g?
F and G are functions such that, oh no, F into G, no. F into G is difficult. These are linear structures. AF plus BG only I am saying. Okay. You are asking another question. No, we are not saying that. Okay. Is this proof clear? AF plus BG, ALF plus BLG. Is it clear?
Yes, sir.
Because integral is a linear transformation, right? Integral of AF plus BG is A times integral F plus B times integral G, and e power minus ST is just multiplying. So this is obvious. Next theorem is if F and G are continuous functions, not piecewise continuous, but continuous functions such that LF equal to LG, what would you like to have? The way I'm stating.
F equal to G.
F equal to G.
Okay, that is true. Part 1 we have already proved verbally, it is obvious, and part 2 is the other extreme. I will not be able to prove this. Okay, some of you will be able to prove this. If you have a little bit more mathematical maturity, you can prove this. It's not difficult, but we will not prove it. Okay, so it requires, an extra argument from a little bit more about continuous functions, which you might not have done in calculus. So we will not prove it, but the theorem is very, very, very important for us. And so this theorem, you have to take it for granted, but it's a beautiful theorem and it's an important theorem. And here continuity is important as clear to you, no? Even if we are not proving this theorem, you can convince yourself that continuity is important. Why? Because LF equal to LG means what? L of F minus G is 0 because of this result. And if L of F minus G is 0, then a certain integral is 0. And from that integral being 0, you are saying that so e power minus st times some function. If the integral is 0, you are concluding that that function is 0. For that, you certainly need continuity, no? Because at one point you can change the function and the integral may not change. Integral will not change, right? If you change the function exactly at one point by making it discontinuous, integral will not change. So from the integral, if you need to conclude anything about the function, certainly continuity you need to assume. Okay, clear, no? That point. Without continuity, you don't have such a theorem.
Sir,
Yeah.
L of F minus G is 0 then.
Yeah.
Is L of F minus G 0? I mean,
Yeah.
can we prove that one? If L of F equal to L of G.
0. If L of F equal to L of G, then of course L of F minus G is 0.
Okay.
Because that is what we have proved here, no?
If I substitute B equal to minus 1 and A equal to 1, then we'll get no. That's right.
Say that again.
If I substitute B equal to minus 1 and A equal to 1, can we get F equal to Z?
Absolutely. That is correct. But from that, it doesn't follow that F equal to G, no?
Okay, sir.
That's what I'm saying. So the content of this theorem is if L of F is 0, then F is 0. That's what you need to prove. That's not obvious. Okay. But I'm saying that continuity has to be there as obvious. Because otherwise, you can take a function. Suppose you have a function such that LF is 0. And you can change that function. Suppose F is 0 everywhere except at one point. For that also LF is clearly 0. No? But F is not 0. So under continuity only you can expect such a result, and under continuity that result is true, and we will not prove it, but we will state it. We have stated it. This is obvious. And the second part is we will not prove, but you should think about the proof if you are interested. But result you have to know. Result you have to know. So note that the continuity are important. Okay, and I explained it already that otherwise, you can have a jump discontinuity, integral will not change, and therefore uniqueness you will not get. And the most important remark is because of this theorem, you have a notion of, you have a well-defined notion of what? If LF is LG, then F is G. So what does that mean? L inverse makes sense, right? If you have a Laplace transform, you can make sense of the inverse Laplace transform and you will get an answer. If you have LF and if you apply L inverse, you will get an F, kind of uniquely. I mean, kind of uniquely in the sense you have to assume continuity, etc. Okay, so there is a good notion of inverse Laplace transform because of this theorem. If this theorem was not there, you could not have made sense of inverse Laplace transform. So that's a remark. So I should put a pause here. Goes by the name Lerch's theorem. Okay, this is the name of the theorem. Lerch is a mathematician, and this is in his name. I think in her name, in his name, Lerch's theorem. So thanks to this, we have a good notion of the inverse Laplace transform. A very, very important sentence in this lecture. Okay. Now let's continue with Laplace transforms. So quickly recall, we have defined the Laplace transform. We have computed the transform of a number of basic functions. We also proved the existence of transform under piecewise continuous with exponential order. And now we want to derive formulas for I want to derive formula for the nth derivative of f. Now, do you see how it is going to come in differential equations?
Yes, sir.
Because I'm going to
Yes, sir.
I'm going to have a formula for the derivative of the function. If I know the Laplace transform of the function, I'm going to have a formula for the Laplace transform of the derivative and Laplace transform of the integral also. Okay, and two beautiful results in terms of L of f. Isn't this getting exciting? The theory of Laplace transform. I mean, when you see the statement, it will get really exciting because you will have the idea how this is going to be extremely useful in solving a differential equation. Okay, so in terms of L of f, we are going to prove this. So here is the first theorem. Suppose f is continuous and f prime is piecewise continuous. I'm assuming continuity of f, and of course, you know, I mean, this goes without saying, because if I have to take f prime, then of course f is differentiable. Okay, and f prime is piecewise continuous on 0 to a for all a positive. That condition I am assuming. And suppose further that f is of exponential order. Okay, because I have used a here, I am changing my a to alpha here. Okay, because it is of exponential order, then L of f prime exists for s bigger than alpha. No, be careful here. Alpha is the order of the function f, not of f prime, not of f prime. But I am saying that L of f prime exists for s bigger than alpha. Okay, s bigger than alpha. For the same alpha, am I claiming that f prime is of exponential order? No, I'm only claiming that f prime is piecewise continuous. I'm not saying that f prime is of exponential order. Without that, I'm saying L of f prime exists. And what is the formula for L of f prime? L of f prime at s is s times LF minus f of 0. So here is a nice formula for L of f prime. Okay, so most important remark here is that, what is the most important remark here? I'm not saying that f prime is of
Exponential order.
Can you connect it with the question that I asked earlier? I challenged you for a game, no? What was the game?
We need to point out an example
Example.
where
The Laplace transform exists even if it's not of exponential
Can you
order.
think of an example using this theorem?
All the f primes.
Find an f which is of exponential order and whose derivative is not of exponential order. This theorem applies, no? So if you can find a function f whose derivative is not of exponential order, find a function f which is of exponential order and its derivative is not of exponential order, Laplace transform exists, right? But the function is not of exponential order. Now, can you think of a function which is of exponential order, but Laplace transform is not of exponential order? What is the only function which we have described which is not of exponential order?
E to power t square.
Now, can you think of a function where in the derivative e power t square will come, but in the function it doesn't create a problem?
Sine of e to power t square.
Very good, excellent. Sine e power t square, if you take, or any such thing, cos e power t square, whatever, that is of exponential order because it is bounded, right? Sine e power t square is bounded and therefore it is of exponential order. But what is the derivative? Derivative is cos e power t square times e power t square times 2t. And there that e power t square will mess it up. It will not be of exponential order. But is it true that sine e power t square will have a Laplace transform?
Sine e power t square.
No, sine e
That
power
is
t
fine.
square anyway will have a Laplace transform. Is it true that the derivative of sine e power t square will have a Laplace transform?
I don't think so.
yes,
Yes.
It will have.
Because of,
According to this one.
this theorem,
because of
this theorem.
Because of this theorem, absolutely correct. Okay, because sine e power t square will have a Laplace transform. It's another question whether you can explicitly calculate it. I'm saying it exists. L of sine e power t square exists, and therefore the derivative of sine e power t square, though it is not of exponential order, its Laplace transform is s times the Laplace transform of sine e power t square minus f of 0. What is f of 0? Sine 1. Okay, and next theorem is if f is piecewise continuous and suppose f is of exponential order, then the integral has a Laplace transform, and you will expect this, no? If you took one derivative, it was multiplication by s up to a constant, and when you integrate, it is division by s, and this is also true when s is bigger than alpha. Beautiful results, right? The effect of taking derivative once is multiplication by s, and the effect of taking integral is divided by s. You see the symmetry in these theorems? If you take derivative, it gets multiplied by s. Of course, there is an adjustment with a constant. And when you take integral, it is division by s, and there is no adjustment with a constant. We will see the proofs today. And what do you think of exponential order? If f is of exponential order, can you think of a function which is of exponential order and the integral is not of exponential order? You gave me an example of a function which is of exponential order, but the derivative is not of exponential order. What about integral? Can they be a function?
ft as t e power t square.
No, you will not get an example, because if you take
Constant function.
integral, and since f is less than or equal to this beyond a stage, that stage it will be less than or equal to e power alpha t dt, right? And when you integrate e power alpha t dt, again you are getting an exponential function, no? So if a function is of exponential order, its integral is automatically of exponential order. Okay, so here you will not get a counter example. Now let us prove.
Sir,
Yeah,
is the gamma function of exponential order?
good question. I haven't thought about it, so you should think about it. Okay, very good question. Good question. You should think about it, because last time also there was this question: does a Laplace transform exist? And if it is of exponential order, of course it exists. Maybe it is not. Maybe it is not, but I did not think about it recently.
Because
So
factorial rises faster than exponential, so probably it should not be.
it should not be is my feeling, but because I am the teacher, I should not assert without some more clarity in my mind. But that's exactly my feeling. I'm not asserting it because I haven't thought about it recently. Okay, but good question. You think about it. Okay, let's prove the first result and then the second result. First result I'm recalling again. F is continuous, f prime is piecewise continuous, and what is given as f is of exponential order, and then I am saying that LF prime exists exactly for s bigger than alpha. Okay, and I have to prove it. So remark, we have already said f prime need not be of exponential order, and this is exactly the example one of you pointed out. And its derivative is not of exponential order, its Laplace transform exists by the theorem. But notice that this is not of exponential order. But let's come to the proof of the theorem. So consider the interval in which f prime has discontinuities. Let us see the proof when f prime is also continuous. Suppose f prime is also continuous. Can you design the proof? What will be the proof? Assume f prime is continuous. Piecewise discontinuity you can easily manage by dividing it and summing it, proving it differently in steps, and by combining all the steps. Assume it is continuous, and if you know how to prove it for a continuous function, f prime continuous, then you know the proof. What will be your step? If f prime is continuous, you have to start here. What is the definition of L of f prime? Integral of
f dash e power minus
minus st f prime
e power minus st times
f prime
t dt, and you can finish the proof. What is the next step?
integration by parts.
Integration by parts by taking integral of f prime. So you will get e power minus st times integral of f prime. But what is integral of f prime?
f.
F. So you are getting e power minus st times f, and you have to evaluate between 0 to infinity. And minus, what will you get? E power minus st integral of f prime minus integral of derivative of e power minus st times f. So you have to do that. And In the second part, you will get S times L of F. And in the first part, when you put the limits, you will get F of 0. Proof is done. So it's an easy proof. I mean, is there anybody who did not understand the proof? Was it too quick? What I'm saying is you just have to apply integration by parts and nothing more. So when you apply e power minus st f prime, in the first part, you will get e power minus st times ft, and you have to apply the limits, and that will give you this part, minus f of 0. And the second part, when you differentiate e power minus st, one s will come, and the remaining thing will be exactly L of f. This is if you are assuming continuous. If it is piecewise continuous, finitely many places you have discontinuities. At each of the subintervals, this proof works, and put all those together, and that is the proof. Okay, so let me put it, I have put it in etc. Tn, you arrange it like this, and this integral 0 to a e power minus st f prime t dt is integral 0 to 1 t1, t1 to t2, etc. One of those you take. Integrating by parts, you will get 0 to a equal to, you can do a to b also. So what will happen is t1 to t2 you will do, and t2 to t3 you will do, and that evaluation of t2 will get cancelled. It will be only t1 to t2. So 0 to a only you will have to do. So that's what is written here. It will be summation I to 1 to n plus 1, right, up to tn plus 1, e power minus st ft from ti minus 1 to ti, plus, now it is the derivative of e power minus st. Derivative of e power minus st is minus s e power minus st. Why don't you see the minus here? Why don't you see the minus here? Derivative
Because it is minus st.
Minus of minus, which has become plus. Integration by parts is a minus. With this minus, it has become a plus, and it is exactly this. But this is Laplace transform, no? This is Laplace transform of f in the limit. So this is s times Laplace transform of f. And what are you getting here? You are getting e power minus st, e power minus stn plus 1, f of tn plus 1, minus e power minus stn minus 1, f of tn minus 1, minus etc. etc. All that when you put together, you will get e power minus sa f of a minus f of 0. Is that correct? You will get e power minus st2
Yes, sir.
minus e power minus st1 plus e power minus st1. So that will cancel. Yes. So you will get e power minus fa minus f of 0 plus s times this. This is exactly what you will get. What is the next step? Take limit as? Take limit as?
A tends to infinity.
A goes to?
Plus infinity.
Plus infinity. So this becomes a Laplace transform, and minus f of 0 is minus f of 0, and f of a is, yeah. So what is f of infinity? What is limit a going to infinity f of a? What do you know about that? What do you know about that? What you know is f is continuous, and f prime is piecewise continuous on 0 to a, and you know all these things. From this, can you conclude something about f of infinity? I mean, what is happening when f is going to infinity? Yeah.
Sir, if we choose s greater than alpha, then f of t power minus st will be less than k e power.
Absolutely,
minus
absolutely. So f may be going to infinity. So f may be going to infinity, but what we know is f is going to infinity slower than e power st. Because of exponential order, f of a may be infinity. I'm not saying that. I'm not denying that. But this whole thing as a going to infinity is 0. Whole thing as a going to infinity is 0 because you have exponential order and a given bound is there. You are assuming s is bigger than a. Okay, so when s is bigger than a, this thing in the limit is 0. Limit a going to infinity, you are getting, and this is true for s bigger than alpha, not a. S bigger than alpha, you have that thing given to you. F of a is less than or equal to a e power alpha t. Okay, so double check that, and that finishes this proof. And why is S bigger than alpha? That's exactly what one of you pointed out. That is where you have, yeah, that is where L of f exists, right? L of f exists exactly when S is bigger than alpha, no? This is what I did not state in the theorem, and I stress that I may not state in the theorem, but from the proof it is clear. When we proved that piecewise continuity together with exponential order will prove the existence of LF, I did have the result S is bigger than alpha. So S is bigger than alpha, only LF exists, and therefore S is bigger than alpha, only LF prime exists. Okay. So S is bigger than alpha, L of f prime exists, and there is a corollary. You can compute L of nth derivative of f. You have to assume that all these are piecewise continuous. All these are piecewise continuous.
So,
Yeah.
sir, in the last example, shouldn't S should be greater than 0 because if S is negative, that the thing will not become 0. E power minus SA.
Yes, yes. So what you have to say is S is bigger than maximum of 0 and alpha.
Sir.
Okay, S is bigger than maximum of 0 and alpha.
Sir, actually, S greater than alpha suffices. We have shown that it converges if S is greater than alpha.
Yes, but what he is saying is the limiting part. A going
Sir,
to
but f of a may decay fast, right?
correct. So that may be enough. So yeah, I got confused. That may be enough. S bigger than alpha may be enough because of decaying faster. Even if S is negative, it should be okay. But please double check. Since a confusion came, please double check. I think this is correct. I will also think about it soon after the lecture. Okay. Let me do the corollary. Suppose all these are continuous, and nth derivative is piecewise continuous on 0a for all a positive. What will be your corollary? Can you guess what will be the statement? I will be computing L of, by induction I can compute L of
Fn.
N minus.
derivative of f, and can you guess the shape? What will be the multiplication? I will take the Laplace transform of f and I have to multiply it with, just take a guess. Multiply with
S to the power
n, s to the power n, and there will be other terms. Okay, so suppose you have to also assume that all the earlier derivatives are of exponential order for the same alpha, and then this exists for s bigger than alpha, and here is the formula. It will be s power n times lf minus s power n minus 1 times f of 0 minus s power n minus 2 times f prime 0, etc. up to f n minus 1 times 0. Now you can see we are not going to use Laplace transform to solve differential equations. We are going to use Laplace transform to solve what? Not differential equations, but can you guess what will be
integral equations.
Integral equation.
No, differential equations only, but not a given differential equations. It should come with this
Initial value constant coefficients.
No.
IVP.
IVP. You know, all these things are going to play an important role. F of 0, f prime 0, all these things. So
Initial value problem.
yes, IVP, initial value problem. So we are going to solve IVP.
Differential equation with IVP.
Yes. So a differential equation together with initial values, we are going to use this method, Laplace transforms, to solve this. Okay. So what is the proof here? It is induction. N equal to 1 we have already done, and assume it is true up to n minus 1, and therefore you would have done this already. So nth derivative is n minus first derivative, one more thing, and therefore this is s of L of n minus first derivative minus this, because this we have already done. And by induction you know the answer for this. So it is s times, by induction you know the answer for this. It is s n minus 1 times LF minus ... this. And therefore, is there a bracket missing here? There's one bracket missing here. So third typo, and you just multiply out, you have got the result. So it is easily done using induction. Let me prove. So I'm exceeding time by 5 minutes, but let me prove the integral also, because it's very much well connected. This is our result. 1 by s is coming. Integral fx dx is also of exponential order. That is automatic, but I'm not using this. This is all that I need. Can you give me the one word for the proof of this? This proof is very, very easy because we have proved for derivative.
Applying integration by parts for this also. Integration by parts for this also.
No.
So the integral will be of exponential order, and then we can apply the whatever.
Apply that before equation, the differential form.
Oh, but what is a key word from calculus?
Applying the differential form for this one.
Integral equation.
Yeah, but
Leibniz rule.
Taking
Leibniz.
Please listen. I am saying one.
Fundamental theorem of calculus.
Yeah, absolutely. I'm saying that I'm going to give the proof of this using the previous theorem. So one of you said this. Please repeat this.
Fundamental theorem of calculus.
Fundamental theorem of calculus is the key word. Okay, so it's beautiful proof. We need to show that L of this is 1 by S LF for S bigger than alpha. And this is given to you after a stage. Okay, you may assume alpha is positive and you are going to take g of t is integral 0 to t fx dx. Okay, so what do you know? G prime equal to f. So g prime t is ft. And you are going to apply except at the points of discontinuities, but that doesn't matter because finitely many discontinuities are allowed. Okay, so g prime t is piecewise continuous and gt is of exponential order. Why is gt of exponential order? Because that is what I made the remark. You should prove that if f is of exponential order, integral f is automatically of exponential order. Therefore, gt is of exponential order. Can we apply the previous theorem to gt now? Gt is piecewise continuous. Gt is continuous. Gt is differentiable. Gt is of exponential order. And g prime t is piecewise continuous. That is enough to apply the previous result to g, right? Agree? So what will be L of g prime? What will be L of g prime? L of g prime is?
S L of G minus G of 0.
Times L of g minus
G of 0.
But what is g of 0?
0.
G of 0 is 0 because t is this. Okay, so very good. You have finished the proof. So L of f is L of g prime, but L of g prime is SLG minus g of 0 and S. So I am, not putting bracket is everywhere. It is understood. Okay, it is bracket of S. This is SLG minus g of 0, but g of 0 is 0. So it is SLG. And therefore you have proved that, and this is all true for S bigger than alpha. So you have proved that LG is 1 by S L of f. But LG is this. So we have finished the proof. In other words, L inverse of 1 by S LF is integral. See, you see a beautiful thing here. If you know the Laplace transform of a function, and if you divide by S, its inverse Laplace transform is given by integrating. And this is going to be very, very useful. We know that inverse Laplace transform exists, no? Tell me once again, why does inverse Laplace transform exist? Is L inverse well defined?
Because the integral is continuous.
Yes, because the integral is continuous. What is the key word?
Continuous.
What is the theorem which guarantees L inverse is well defined?
Lerch's theorem.
Lerch's
Lerch's
theorem.
So if you have to give me just one word, like Abel's identity, one word was Abel. What is one word?
Lerch.
Lerch. Okay. So that's the end of today's lecture. We will, maybe I went a little bit fast towards the end, but the concepts are so clear and I wanted to combine integral and differentiation in one lecture. And that's why I took a little bit of time. And let me stop here and I will revise this and continue in the next lecture. I hope already you are feeling the excitement of Laplace transform. All these are going to be very, very useful. What we will do is once you have an IVP, you will apply the Laplace transform to the IVP. And when y and derivative is there, you will convert it into this thing. And all these things you can plug in because all these are given in your IVP. So you will have a polynomial in S because L of f you know. Okay, L of f is what you are going to find out, right? Because f is the unknown, y is a solution. So L of f you are going to find out. by converting the IVP into a polynomial equation. Solve for that, and you will get L of f. And once you get L of f, how will you get f? By taking the inverse Laplace transform. Okay, so that's how we are going to solve IVPs. Anyway, we have more lectures. We will do it slowly and with more examples. And that is the end of today's lecture. Let me stop sharing. And if you have one or two quick questions, let me stop recording also.